In exercise 2a, we will now explain the functionality of the Bayes or Bayes classifier. So we start with Bayes' theorem. And that you already know from statistics. So the probability that y is of a certain class, given the data that we have, is equal to the probability of to have the data if a class is given times the probability of the class itself divided by the probability of the data itself. So our estimated class is the argument that maximizes the upper part here for every I. And now we have to see how do we get the individual parts here. And how to get y, the probability that y is a certain class is very intuitive. That's just a proportion of the class. Now we have to get this part, and this is a little trickier. We will use our likelihood function. So first we have to make an assumption about the data, and it is that the data is, so our features are normally distributed. And then we can use the following likelihood function or density function. I mean, you know this already from the lecture. So maybe skip this part until I'm done. And those mu, for example, or maybe I should wait until I'm finished, so the people that skipped won't have a disadvantage. So basically mu is just our our mean, like we estimate that with the sample mean, and we estimate sigma with the sample variance. So all of this is estimatable. And now we can basically use three different methods. So the first one would be if all the sigmas, like all the covariance matrices for all M classes are equal, then we can use the linear discriminant analysis. If they are unequal, then the quadratic discriminant analysis or if they are all equal, and diagonal, so that means that all values but the ones on the diagonal are 0, then we can use the naive Bayes classifier. Now to make things a little easier, we can derive the discriminant functions. Which are basically where we just take the logs of the density function and then neglect everything that is not dependent on the classes. Then you get for the LDA following function. And for the QDA, this quadratic one. And for those, you can much more easily find the value for m that maximizes this function. And the nice property is that if you can maximize, or the argument that maximizes the respective discriminant functions will also maximize the density functions, and will therefore be that argument that should be the class that we find most likely for a given x. So that's our prediction then in the end. So get the largest value. For the discriminant function. So dependent on which one you use, LDA or QDA, which depends on your sigmas. This will get you of the likelihood and therefore the highest probability, or the class with the highest probability. And that's what we want to find out in the end, which what class is most likely for a given x.